All right, we will now be moving on to a talk from Adam Disney. He will be discussing file level erasure coding in Lustre. Adam has worked as an HPC storage system engineer at Oak Ridge National Lab since 2018. He has a background in neuromorphic computing, erasure codes, HPSS development, and recently has started in Lustre development. So we'll go ahead and pass it over to Adam. Yes.
All right. All right, so I'm going to talk about file level erasure coding in Lustre. I'm going to go over essentially, sorry, I would use the background, but it doesn't like my white background, my plain white background with my plain white face. So it's really messed up. So I'll go over the current progress where this is. I'll give a brief introduction to erasure coding. Often when I talk to people about erasure coding, it's sort of like they have a vague idea what it is, but not really. So that it's important to understand at least basically what it is to understand how it applies to the progressive file layout in Lustre. And then I'll go over brief, how you would use it and some limitations and pitfalls that are going to be in this initial version. So the original patches were written about a year or two ago by Bobby Jam. So you might be thinking, well, why am I talking about this? Well, a little less than a year ago, I was asked, a little less than a year ago, I was asked if I could work on this because I guess Bobby had to do other things. So it was sort of dropped before it was finished. And I have a background in erasure coding, but none in Lustre. And they were like, okay, well, that's fine. You'll learn it. So here I am. This is my introduction to Lustre is working on this feature. So what have I done with this? Well, I've of course inspected these patches to see, figure out how it works in Lustre and all of that. I ported it to the master branch roughly just a few months ago. I have the hash for that checkout if that's important to anybody. So it's mostly current, but it's a little bit behind. I've fixed a few bugs so far. Noticed things with the erasure coding specific things because I have experience with that. And just a few other minor things that cropped up while running the regression tests, like logic errors or a null dereference. So I have run regression tests against Sanity. Yes, RAID 6 is a form of erasure coding, yes. So I have run regression tests, the Sanity shell script, and so far it doesn't appear to break anything with the code integrated in. And now what I'm trying to do is get the feature to actually work so that I can develop tests and fix the problems with it. So currently it appears to be something minor that I'm just unfamiliar with. At least that's my hope, because we're hoping to get this into the 2.15 release. I would guess it's about 80% complete. So why do you care about this feature at all? So first of all, in Lustre, there's file level replication already. So what this is for is essentially you want to put your file into Lustre and you want to make sure it doesn't get lost. Your data isn't lost. Well, maybe you're thinking, well, why isn't my Lustre installation using reliable storage? Well, that might be too expensive for your particular instance, or it may be expensive in the sense that you don't necessarily need the reliability on all of your files, just some of them. And so you move that responsibility up to a file level rather than at the base level, at the storage level, the device level, I guess. So essentially what file replication does, right? You just make multiple copies, really easy to understand. But the downside to that is that every copy is 100% overhead. So what does erasure coding do? It solves the same problem, but essentially what you're going to do is calculate some coding data that's going to be stored with your file in Lustre. And so this coding data takes some time to calculate, but it generally requires far less space than just making copies of your file. So the code that, if you've ever heard of erasure coding, you've probably heard of Reed-Solomon codes because it's the most common and one of the oldest. So, and it's going to be the one that's used in this feature. So how it works is essentially you're going to pick a K and an M. The K is going to be the number of data blocks per stripe, and the M is going to be the number of code blocks per stripe. Now, these blocks, the data blocks and the code blocks, are the same size. This isn't the erasure code. The coding isn't something like a hash that's small. It's rather large. And basically, you can pick any K plus M code that you want. That's obviously that's like saying you can store all the files you want. There are limitations, but practically you can pick anything you want. And what it does is for any K plus M stripe, you can recover all K data blocks from any K blocks. So here's an example. Let's do 4 plus 2, where K is 4 and M is 2. So here we have in blue the data blocks, and the green is the coding blocks. So how do we get this? Well, it involves some matrix multiplication. So essentially, we have an encoding matrix where the top portion is an identity matrix. If you're rusty on your matrix algebra, that just means it's like multiplying by 1. So you get your data back through this identity matrix. But then on the bottom, we have our encoding rows. And these constants that are these lowercase letters here, they are picked with care, but it doesn't really matter to understand exactly how you pick those. Just know that they are chosen with care and you can generate those easily. And when you do this matrix multiplication, you end up with your coding blocks that you need. So what happens when there's a failure? Well, suppose we lose data blocks B and D. So if we change the original equation to take the rows out that generated the B and D, then this is what the equation would look like. So we just took out the 2 rows in the identity matrix that gave us B and D. So what we have is the right side of the equation, and we want the data on the left side. So the constants that we picked in the coding portion were chosen such that any square submatrix, essentially if we take out 2 rows, any 2 rows, that square matrix can be inverted. When you invert that matrix, it's the multiplicative inverse. And so when you multiply both sides by this inverse, you get your data back. And that's basically how it works. It's pretty simple conceptually, complicated in practice, of course. So how does this compare to triple replication? Obviously, it saves you space. That's what I was mentioning before. So here we have the 4 plus 2 example versus a triple replication. Now, in both cases, it can survive any 2 blocks being deleted. So I can choose any 2 blocks from either version, and I will still have the entire file. And the triple replication can even go as far as some 3 through 8 failure cases, but not all of them. So in the worst case, they're equivalent. They can survive any 2 blocks failing. But obviously, the Reed-Solomon code, it takes up half the total space, or only a quarter of additional space. So this is the reason to use this erasure coding. So how does this apply to the progressive file layout? So I guess the feature should really be called component level erasure coding, because it applies to a component in your file. So here in this example, I have, we're using the set stripe command to create a new file with this stripe setup. So when you define it, you have to say dash capital E with some ending offset. And then that says from the previous element up to this point, I want this particular layout. So since this is the first one, it's going from 0 to 4 megs. And I'm saying I want the stripe size to be 1. And then for the next element, I want it to go to the end of the file, and I want the stripe size to be 4. So that's normal stripe progressive file layout. But then to use this feature, you will add on additional components where the -E will have some matching value to a data component. So here I'm saying EOF again, because I want this one to apply to the element that ended at EOF. And I have to specify that it's an erasure coding layout. And then I have to pick my K plus M essentially. That's what data count and parity count are. Now, you can technically pick any K you want that's equal to or less than the stripe size of the data that you're making erasure coding for. But it generally makes sense to make it match. So you can see here, and to point out that in this particular instance, I'm not protecting the first 4 megs of this file. So it's important that if you want to protect the entirety of the file, you have to apply one of these to every component in the file if you have multiple different layouts throughout the file. So here, it's just 4, 5, 6, 7. Those are the 4, 5, 6, 7 blocks, and then we'll have the parity for 4 through 7 and another parity 4 through 7, and so on. So how do you use this? Essentially, you do what I was showing in the previous example. You're going to set the stripe on some file, and then you write to this file, and then you'll have to run a resync, a mirror resync. So similar to the replication feature. So it doesn't do this as you write. Essentially, you'll have to, when you're done writing your file, you'll have to run this resync. When you're reading the file, if there's some sort of failure, like the client can't get to a particular block, it'll figure out on its own, okay, well, there was only one block missing, so I can read a parity block and recalculate what that block is, and then just present it as normal. So it does it all on its own. And of course, if you modify that file, you'll need to make sure that you resync that file, or you won't be able to recover data when it's lost. So some of the limitations in this are, there's no automatic data replacement, meaning, so say there is some permanent reason that that block is down. It currently doesn't do anything to fix that. And I'm not clear yet how you would be notified, but someone would have to go in and essentially, I guess, migrate your file to a new layout. To get it to copy the data into another file. There's also no automatic updating of the parity, as I was pointing out. You have to do that yourself at some point after you've done writing the file. There's also a concern that the encoding and the decoding might be slow in this first version. And that's because the original design was to use the Intel's ISAL library to do the erasure coding, but that's a user space library, and we're working in kernel space. So that's not a good idea. And there's really no kernel space library to do exactly what this does. So the easy solution, since there's a permissive license on the ISAL library, is to essentially just copy the straight C implementation of the erasure coding library. This excludes all of the optimizations that has with inline like SIMD instruction optimizations, because that has a whole nother figuring out how the build system works exactly and all of that. So this first version is simplified by just having the straight C sort of unoptimized version, but then ultimately eventually have some replacement for this, like a general loadable kernel library that would do this type of thing so that anyone could take advantage of it if they needed to. And also data placement is, you have to be careful with data placement. And this is also a concern with the file level replication. But let me show you what I'm talking about with data placement. So we're taking the exact same picture that I showed before, but what if it was set up in these OSSs? So we have these 3 OSSs, and these are how the OSTs are set up. In this example, if I were to somehow say OSS 1 goes completely down, well, that's 3 blocks out of my stripe, which means my file's unaccessible just by that one failure. Or even all of these OSTs might be on the same appliance, for example. So if that goes down for some reason, you've lost your file still. Generally, you want each of your blocks in your stripe to be on a separate failure zone, essentially. And I believe there are Lustre, there's OST pools that can be defined, and you can sort of work around it in that way by defining pools in the proper way. But you still have to be very aware of the topology for this to work properly. Because even in some of my initial testing, it looks like by default, if I don't do anything, these parities actually end up on OST1 and OST2, which is a bad idea. So you have to do something to be smart about it. So that's basically the feature. I'd like to thank James Simmons and Rick Moore at ORNL for Lustre lessons. Like I said, this is the first thing I've done in Lustre, and they've been a whole lot of help teaching me how these things work. And of course, the obligatory acknowledgement to the lab.
Great, thank you, Adam. That's very good work. All right, so let's start with a few questions that came in through the chat. Do you have plans to write some documents to explain these ideas, specifically the recovery part? I would comment that these slides are probably a great start to that, but I assume something would go into the Lustre manual. Right. Yes, definitely there should be something in the manual once this is put in. Right now, the main focus is obviously getting it working, but definitely can put some documentation in there. All right, let's see. Alistair was commenting on why you're using multiple capital E's. Why not add the erasure coding info within an existing capital E? I think that, so I didn't design that syntax. That was part of the design previously. And I think the reasoning for it is that it's technically a different component, so it was easy to get it to work in that way. So if I were to say -E, if I were to include the erasure coding layout to one of the other components, then it's different from how you normally do it, where each E equates to one component. This particular one would all of a sudden be 2 components. And I'm not sure that probably throws off a lot of the logic that already exists in the LFS tool, in the set stripe tool. But it's true, that could be a bit easier and more clear, I guess. I agree. I even got caught up on it initially myself. All right, let's see from Corey. Why do EC per PFL component versus with FLR for the whole file? Well, part of it is because you have different striping levels per component. So like I said, if I try to, like I had my example, I'm still sharing, aren't I? Right here. So if I apply that 4+2 code to this particular layout,
Well, the first 4 megs will have all 4 blocks on the same OST. And so it's not really protected anymore. Like that one OST going down will still lose the file because I'll lose 4 blocks all at once. So we're sort of using the fact that the stripe count in the data component is laying out the blocks as we need them. And so you could generically say, you could have one erasure coding that applies to all layouts as long as that one erasure coding can apply to all of the, layouts, components. So you would have to make sure, so like in this case, I couldn't say 4+2, I'd have to say 1 plus something, or change this first element to have more stripe width.
Yeah, I think building off of that, could you combine EC layouts? So if we had something like DOM enabled, could I say mirror the first megabytes on metadata servers, but then once you hit the OSTs, we move to a +2 or something along those lines?
I think currently you can't really apply any layouts to DOM files, if I'm not mistaken. So it's always single striped. But yes, the additional, well, you could do that I guess what you were saying with this example. So like the first 4 megs is on DOM, and then the rest of the file is erasure coding. So yeah, you should be able to do that.
Cool. We have a couple more minutes. If there's no more questions, I can ask a few more. So based on the performance that you've seen, are there any plans to leverage maybe on compute side accelerators like NICs with FPGAs or just servers that have FPGAs in them to help with the EC?
Okay. So using some sort of accelerator, no. So I haven't been able to performance test yet. There's a whole lot of performance that we're dropping with the not being able to use the full ISAL library optimizations, and those should be fast enough to keep up. But it's always possible that, you know, something like an FPGA, that'd be very specific in the code, but it's possible.
Or it could be like a check if you have it available. Kevin, do you have a question?
Right.
Sorry, I missed that, Kevin. Kevin asks, is there a path to providing failure domain info into the EC component?
There's currently not. I don't, in my discussions with James Simmons, I don't think there's really any way for you to, I guess the OST pools are the best thing you can do. So it might be possible to get that info when it's initially figuring out the layout. Well, I guess you explicitly give it to it. But yeah, you sort of have to know the layout ahead of time. So I guess one thing you could do is define a bunch of OST pools where every element of the pool is independently failing. And so you have a bunch of those, and then that way you say, for this component, use this pool, for this component, use a different pool. And then that guarantees that they're all separated and on different things.
Awesome. Well, thank you for your work. I think it's a great contribution. Glad someone is picking up this work, and thanks for presenting it.
Thank you.